I'm Professor Greg Pasternak from the University of California at Davis, and my presentation today is titled Geomorphic Covariance Structure Analysis of River Terrain for Process Evaluation and River Design. Today, academia is very focused on the idea of passive restoration. That is, that if you just get out of the way as much as you can, and then let the upland drivers of flow regime and sediment supply go to work, that they can then propagate through a watershed and drive the fluvial processes to return the system to a more naturalized condition. Now, I would argue that there's a significant problem with this approach, and that is that it's adjusting the drivers or the input conditions without recognizing that the underlying partial differential equations of fluvial processes are equally as sensitive and governed by the boundary conditions. So just removing one little boundary condition like a levee or changing one little upland driver is not enough to institute what you need. And what you need is to recognize that rivers are part of an entire natural topographic regime. This regime is a comprehensive boundary condition on the system, and it's only through mindful understanding and manipulation of that regime that you can get processes. And so therefore, I would say that passive restoration is more of prayer-based restoration, not process-based restoration, because they don't know what they're getting. They're just instituting things and seeing what happens, and hopefully through many trial and errors that will build up an understanding. But that really isn't what understanding is about, and so it can't be what process-based is about either. So how do we get to a process-based understanding and design capability accounting for natural topographic regimes? Well, first we have to recognize that rivers have been completely devastated across their entire topographical regimes. This just shows a really bad scenario of mine waste totally erasing the landscape and creating something new, as well as with chemical degradation. But across mountain, suburban, urban landscapes, we have terrible problems with topographic regimes that water and sediment alone just won't be able to fix in a meaningful period. And especially when you continue to have humans involved, and we have to be able to predict and understand what the natural dynamic regime should be and what can be self-sustainable and what can be sustainable with continued human activities. Traditionally, the understanding of the natural topographic regime simply involved figuring out the central tendency of one channel dimension. So assuming that rivers are just one shape of channel in their cross-section, and then relating its attributes of width and depth, for example, to the bankful discharge. So this research was really important for basic science, but it's not even remotely close to the foundation of what river restoration needs to account for. And that's why the landform mimicry from 1980 to 2010 or so, and sometimes still ongoing, it just doesn't work. You can't just mimic the central tendency. What's more interesting in this empirical relationship here is all of the noise. But the noise isn't noise. That's the thing. Statistically, people thought of it as noise. Each point on here represents a place where there are processes causing that deviation from regional functionality. And that is not arbitrary or noise. That is the driving processes that make that site alive. And so we need to understand that variability, control it, and design it. For example, here's 20 kilometers of a river in California where I've plotted 0 as the mean width of the river and then plotted the standardized variability here. So going from a standard deviation of 2 times the standard deviation negative to 2 times the standard deviation positive. So very narrow to very wide cross sections. You can see there's a tremendous amount of variability. So if I took the average of all this and made one point here, not only is that one dot different from the regional line, but that the reach as a whole internally has a lot of variability. And that's something also that river restoration just hasn't dealt with. We have to be able to understand and design variability at many spatial scales. So how do you do that? Well, I'm going to show you that, but it's important to first understand that sub-reach scale geometric variability is the most important, exciting, and challenging part of designing a realistic river. Up until now, river science and design have largely ignored subreach scale variability, and it really is time to change. And there certainly are people who are diving into this now. And then finally, the software that we've been building for many years now, called River Builder, has variability as its core design capability. Okay, so when we want to design a river now and moving forward, we have to have a framework that can allow us to design that variability to then be able to go out and build it to control the processes that we want to have, given the flow and sediment supply regime that realistically any location is going to face. And we do that using a geometric design framework. That means that we're going to directly reproduce the three-dimensional shape of river elements with equations. While this could be mimicry if used that way, it could also be process-based if we know what boundary condition regime drives different processes, and we certainly do. With this approach, we can make an exact representation of the topography that we want to have. It can be scalable across any dimensions. We can add or subtract many elements, as I'll show you shortly. And we already know that many geomorphic and ecological processes can be written as geometric functions. Also, compared to trying to design using morphodynamic models, this approach is uninhibited by any assumptions about how rivers ought to work. We can just explicitly write that three-dimensional shape and then interrogate it for its functionality. So the purpose of the study in this presentation is that I want to show you some of the procedures that we've been working on and illustrate a little bit about the software that we have for designing science-based, self-sustainable topographic variability patterns for rivers spanning from base flow to flood flows. Now, I'm not a big fan of reference reaches, but reference reaches are still really important to understand how rivers in a particular region work. And so it can be helpful to be able to reverse engineer the variability that's existent in your reference reaches. But then I also want to show you how we can work from scratch to make process-based designs with our River Builder software. So for example, let's take a real reach here along Happy Canyon Rose in Santa Ynez. I picked this because it's a dry river reach so we can see the structure pretty well. We can draw the thalweg down that river corridor, and I can even make the thickness of this line about the bankful width of the channel. If we come across here, we can see a schematic representing the multiple vertical layers of the river corridor. So maybe you have a really small base flow, then maybe you have a little bit higher base flow, and then that's all inset within a bankful channel dimension, which itself is inset within terraces that could be offset at different stages on the left and right banks. So if we start with the base flow channel alone, we need to be able to have a base flow channel that can sustain the species that exist during base flow conditions. To do that, we can create the width and bed elevation series. And here's an example just for this river. Here's the width series. And you can see that there's a lot of high frequency and low frequency fluctuations. Well, we can take this series and do a harmonic decomposition to extract the underlying constitutive elements that can be added together to create that complete pattern. Now, you may need 20 to 100 of these constitutive elements to get there, but you can get there. And this just shows 5 of them to give you a feel for that. Then we can go up to the flood flow. And so I've just sort of sketched out roughly, kind of like a flood pattern here. This isn't the real pattern, but it gives you a feel for it. We can then layer on again the thalweg, and we could then extract a width series going down this river, to see how the cross sections change. And we can see that here too, it's not a uniform valley. The valley gets wider or narrower as you go along. It generally is getting wider, but there's a lot of undulations here controlled by the valley width that's present. And we can deconstruct that as well into its constitutive elements. So what I'm showing you is we can take a reference reach, we can break apart its things, and it's not just width. We could do bed elevation, we can do sinuosity or like curvature down the river, we can do presence of wood, boulders, like whatever we want, and then we can reconstruct those things in River Builder. Just to show you a different site, here's the South Fork Eel, which is one of the sites that we have along this river in Northern California. You can see that there's a really rough bed in here. There's also a base flow channel that's then nested within a bankful channel within a relatively confined canyon. So in this case, we went out and surveyed the topography of the site to get a real representation of it. It's not a great survey, it's a feature-based survey approach. And then from there, we wanted to see if we can reconstruct a two-stage pattern here, the bed undulations and width undulations for the Baseflow channel and the bankfill channel. And so when we extracted those series and then recreated them in River Builder, we get something like this. We get an archetype that captures the essential changes within the channel and also includes that gravel cobble roughness of the bed. There's a lot of reasons why you could use an archetype like this to help with your design hypothesis testing or just scientific research of what general channel types will behave like. Now, how do we go from scratch? So get away from reference and get to really process-based design. Well, to do that, we go through a sequence of steps in River Builder strongly driven by our conceptualization of what processes should be at place. And so we can take a river and divide it into three two-dimensional planes, a profile, a cross-section, and a plan form. And we need to characterize each of those at different spatial scales. We begin in the channel. You can see down here 3 different types of channel cross-sections for the Baseflow channel. We could have a simple U-shaped channel. We could have a channel that asymmetrically slashes back and forth as the river is meandering. Or we can have geometric designs consistent with like urban and suburban settings or agricultural settings. We then nest that Baseflow channel within a larger channel and valley context, looking in the cross-section. You can specify as many breakpoints as you want, and then using those breakpoints, you're basically characterizing levees, roads, side channels, yazus, whatever you want. You can create all these things, and then independently, the left and right can be made. And the channel is then nested within a sinuous valley, which itself has a lot of dynamism if you want to account for that. Once you have this pattern, you project it into 3 dimensions by assigning to each of these breakpoints a contour that is governed by a geometric variability function. These functions can be locked together, and that's really the key element that controls processes, is understanding how to lock the Baseflow channel dimensions to the bankfill channel dimensions, the flood channel dimensions, and so on. And then finally, we just render that into 3 dimensions. We have many geometric variability functions. I'm not going to read through this list, but if you want, you can pause here and look at that. And these can be applied to both the bed elevation as well as the meandering, and then the third would also be width functions. River Builder includes many individual features. You can have different boulder sizes and as many of them as you want. You can have overall topographic roughness. We have steps and waterfalls, and then individual man-made structures if you want. But most importantly, we have to link these series together. And what I mean by that is here is a profile down a river of the width series in blue and the bed elevation in series in red. And you can see that the bed undulations and width are tightly coupled. This is not by accident. This is how rivers actually function by using this topographic variability to drive morphodynamics. We can use this in design with this concept geomorphic covariance structures. A GCS is a spatial series of the product of 2 standardized variables along a river corridor. So for example, if I take the width and bed elevation and multiply them together after standardizing them, then I get a series like this. And this series is diagnostic of the kinds of morphodynamics that are present. When you've looked at these enough, you immediately know for a particular channel type whether a river has a degraded or naturalized GCS and what you need to do to restore that. Just as a test for you, if you just think about the fluid mechanics, here are two-stage topographic regimes. One of these has a self-sustainable pattern and the other one does not. Is it the left? Is it the right? I want you to pause and think about that. If you were to put a base flow and a flood flow through here, which of these would fall apart and which would be sustainable? So in conclusion, passive restoration is not necessarily process-based. I would argue that it's prayer-based. Process-based means that you can make design hypotheses that will predict what will happen. If you can do that just conceptually, go for it. If you can do it with numerical models, even better. But you should understand what is going to happen and why. If you can do that and you're just passively doing things, then perfect, great, then you are process-based. But if not, I recommend that you consider geometric channel design using sub-scale variability functions that really take the whole thing to a new level to really understand how a river works. Thank you.